Hello everyone, welcome to Extramarks live classes. In this session today, we are going to discuss about interconversion of states of matter. Yes, what we are going to discuss is how we can change state of a matter from solid to liquid, liquid to gaseous, and the reverse of it. We know that substances exist in mainly they exist in three different states. So how we can carry out the conversion of these states whenever we desire so, or when, like how it happens on its own. Okay, so in today's session we'll be discussing about a number of associated processes like melting, freezing, vaporization, which also which refers to both evaporation and boiling. We'll also understand about volatile and non-volatile liquids. We will talk about latent heat of fusion and latent heat of vaporization, and the remaining processes like condensation, sublimation and deposition will also be discussed, followed by discussion on liquefaction of a gas. That means we'll understand how a gas can be obtained in its liquid state. So a substance which exists originally in gaseous state, how can it be converted to its liquid state? By changing the temperature and pressure. So whenever we talk about change of state of any matter, we should remember that various states of matter are interconvertible, and how we can change one state of matter into another state. This is possible if we change the temperature and pressure. That means by bringing about a change in the temperature and pressure, we can change the state of the matter. And this phenomena of change of a state from one state to other state on changing the temperature and pressure of the substance is known as interconversion of states of matter, and this is what we are going to discuss in detail in today's class. Let's start our discussion with the basic interconversion of states of matter. That means first point that we need to remember is physical state of any matter can be changed by changing the temperature and pressure. So these are the two important parameters. Change in temperature or change in pressure will result into change of physical state of matter. And have a look at this particular chart here. This particular chart here compiles all the processes associated with interconversion of states of matter. We are going to talk about conversion of solid to liquid, liquid to gaseous state, and the reverse also. So we name the process as melting for conversion of a solid to its liquid state, and this becomes possible when we heat a solid. And the reverse process, that means the conversion of a substance from its liquid state to solid state, is known as freezing. So when we provide heat to a substance, it melts. But when we cool a substance, we decrease its temperature, it solidifies, it freezes, isn't it? So melting and freezing are opposite of each other. Similarly, when we heat a liquid, it moves to the gaseous state. For example, water, when it absorbs heat or we heat it intentionally, it moves to the gaseous state. The process is known as vaporization. Vaporization, as I told you, refers to both evaporation and boiling. We will understand the difference in between evaporation and boiling in the upcoming sessions. And the reverse of conversion of any substance from its gaseous state to liquid state is known as condensation. So these are the connected process. Like solid will melt, it will convert to liquid, liquid will vaporize, it will convert to gaseous state. But there are a few substances which on heating directly moves to their gaseous state, bypassing the liquid state. The process is known as sublimation. And the reverse, when you see a substance moving from its gaseous state directly to the solid state, is known as deposition. So we are going to discuss all these processes and related concepts. Which processes? Melting, freezing, condensation, vaporization, sublimation, deposition in detail. Let's begin with melting. Melting refers to conversion of solid state to liquid state. That means change of state from solid to liquid is known as melting. And we can define melting as a process in which a solid changes into liquid by absorbing heat at atmospheric pressure. That means we are not bringing about any change in the pressure around the substance. What we are doing is we are simply changing the temperature. So as soon as the temperature increases, solid the solid changes to liquid. So this particular process is known as melting. We can also call this process as fusion. What we can call it? We can call it fusion. For example, when I talk about the solid state of water, that is ice. Ice converts to water, which is the liquid state, on heating. So we say that it is the melting of ice that is taking place. And what do you think? Will the ice melt at any temperature? No. The ice melts at a specific temperature known as melting point. What do we call it? We call that specific temperature as melting point. So how can you define melting point? You can define melting point as the temperature at which a solid substance melts to change into liquid at atmospheric pressure. So a solid does not melt at any temperature. There is a specific temperature on which this process of melting takes place. In case of ice, the melting point is equals to 0 degrees Celsius. But for different liquids, the melting point is different. So each and every solid substance has a characteristic value of melting point. We need to heat a solid up to a specific temperature before it starts melting. So if you take a solid, say we take solid X, we start heating this solid X, it will start melting. It will not start melting as soon as we apply temperature. No. As soon as we apply heat, what will happen? The temperature of the solid will start rising. And at a specific temperature, that solid will start melting. So what happens at that temperature that we call as melting point? What actually happens at melting point? So this we need to understand. So I'm going back to the previous slide. The question is, what causes melting? What happens when the solid substance reaches its melting point? See, when we heat a solid substance, what happens? The kinetic energy of the particles increases. We know that inside the solid, the particles are at a fixed position, isn't it? They remain tightly packed with each other and their positions are fixed. We have already studied that particles inside a solid are not capable of leaving their fixed positions, but yes, they definitely vibrate at their own positions. So as soon as we start heating a solid, its kinetic energy starts increasing. And with the increase in kinetic energy, the frequency and the magnitude of vibration both increases. So we can say that the particles inside a solid start vibrating at a greater speed and at a greater frequency when we heat a solid. We keep giving heat, the frequency as well as the magnitude of vibration will keep on increasing, and a point will come where the solid particles will be able to overcome the forces of attraction existing in between them. Okay, we know that the particles inside solid are held together by strong interparticle forces of attraction. If a substance wants to move from solid state to liquid state, these attractive forces needs to be overcome. And that becomes possible with the energy that we supply. So the energy supplied helps to overcome the forces of attraction existing in between particles, and the particles leave their fixed position and start flowing. This is the property associated with liquids. Liquids can flow. The particles in a liquid can flow in a group. Okay, they can move from one place to another place in a group. If one particle goes in one direction, all the other particles will follow that particle. So their positions are not fixed, but yes, they cannot leave the group. They cannot move in random directions, but yes, all the particles become free to move from one place to other place. That is why we say the liquids can flow. So when we heat a solid, due to increase in the kinetic energy, the vibrations increases, and finally the interparticle forces of attraction are overcome and solid converts to liquid. So at melting point, the temperature at which solid substance melts and changes to liquid state at atmospheric pressure, what happens? The kinetic energy becomes sufficient to overcome the forces of attraction. So the value of melting point actually helps you to understand the strength, or say it gives you an idea of the strength of attractive forces existing in between the constituent particles inside a solid. Higher the melting point, that means higher is the magnitude of attractive forces. See, if two particles are held together through strong forces of attraction, more energy will be needed to overcome that attractive force, isn't it? If the attractive force is weak, less energy will be sufficient to overcome the attractive force. But if the attractive forces are strong, more energy will be required to overcome that force of attraction. So the value of melting point is the measure of the strength of attractive forces existing in between the constituent particles in a solid. Higher the melting point, more will be the attractive forces between the constituent particles. So just by looking at the value of melting point for a substance, you can comment on the magnitude or say the amount or say the strength of attractive forces existing in between the particles of that particular solid. Okay, so this is all about the melting and melting point. Now coming on to a very important term, that is latent heat. See, this latent heat term is related to phase change. Phase change means when a substance actually undergoes state change, when it actually undergoes phase transition. I told you that when we start heating a solid, it starts melting only after it reaches a specific temperature. Before that, what was happening? The temperature was increasing, but as soon as the solid starts melting, its temperature becomes constant for some time. Yes, it has been observed that whenever we melt a solid or we boil a liquid, as soon as the process of melting or boiling starts, the temperature becomes constant for some time. And we continue heating. We are not stopping the heating. You must be getting an idea that as soon as the temperature reaches the melting point of the solid, we stop heating. No, we do not stop heating. Although we are continuously heating it, the temperature is not increasing. So where is the extra heat going? That extra heat is known as latent heat, and that extra heat is actually required, or say that extra heat is actually utilized in overcoming the attractive forces existing in between the particles. So as soon as the process of melting or boiling starts, the temperature becomes constant for some time, and the extra heat that we give to a substance, maintaining it at its melting point or boiling point, which is utilized in overcoming the attractive forces, is known as latent heat. So the temperature becomes constant because the heat is being utilized in overcoming the attractive forces, and hence temperature is not increasing. So that heat is known as latent heat. How do we define latent heat? We define it as the minimum amount of energy that is required to change the state of a substance at the transition temperature. Now, why we are calling it transition temperature? Because we are talking in general for now. Latent heat, this concept of latent heat can be applied to process of melting as well as to the process of vaporization, to the process of boiling specifically. But here I am not using the term melting point or boiling point because we are talking in general. So at the transition temperature means at the temperature at which melting starts or the temperature at which boiling starts. As soon as a liquid will reach its boiling point, the temperature will become constant for some time. And it will remain constant until all the liquid converts to gaseous state. And during that period, during that time period when the liquid is actually converting to the gaseous state, the extra heat which is supplied is known as latent heat. And why do we call it latent? We call it latent because latent means hidden. It seems that the extra heat is being hidden somewhere. We are not able to see any visible change because of that heat, because it is working at the molecular level. It is working at the particle level, and we cannot see the particles of a matter, isn't it? So that is why we call it latent heat, meaning hidden heat. So latent heat is of two types: latent heat of fusion and latent heat of vaporization. This term is applicable to the process of melting, and this term here is applicable to the process of boiling. In today's session only, we are going to understand them in detail, starting with latent heat of fusion for now. Since we are discussing the process of melting, we'll be talking about latent heat of fusion, and we'll understand with the help of ice to water conversion. Okay, suppose I take some amount of ice, some quantity of ice in a beaker, and I start heating it. The temperature of ice might be like somewhere below the 0 degrees Celsius. So the initially temperature will rise. Suppose the temperature initially was -3 degrees Celsius, and I start heating ice from this level. After some time, the temperature will become 0 degrees Celsius, which is the melting point of ice. At this particular temperature, the process of melting will start and the temperature will become constant. Okay, so the zero, as soon as I start heating, the temperature initially rises, but as soon as it reaches the value of 0 degrees Celsius, it becomes constant. And at this particular moment, what happens? The melting starts and the temperature will remain constant at 0 degrees Celsius until all the ice in the beaker has melted. Until all the ice in the beaker converts to liquid state, the temperature will remain same. And we are continuing the heating. So, the amount of heat which is required to convert 1 kg of ice, or in general, if I talk about latent heat of fusion, let's define it in general, not just for ice. For any solid substance, the latent heat of fusion is the amount of heat which is required to convert 1 kg of solid into liquid state at atmospheric pressure and at its melting point. That means you need to maintain the solid substance at its melting point, and maintaining the temperature at melting point, the amount of heat which is required, that heat will not be utilized in increasing the temperature. That heat will be utilized in overcoming the forces of attraction existing in between the particles of a solid. So, latent heat of fusion is the amount of heat required to convert 1 kg of solid into liquid at atmospheric pressure and at its melting point is known as its latent heat of fusion. Different solid substances will have different value of latent heat of fusion. For example, the latent heat of fusion for ice is 80 kilocalories per kg. What does this mean? This means that 80 kilocalories of heat energy is required to convert 1 kg of ice into liquid state, maintaining the temperature at 0 degrees Celsius. Okay, so that is what this particular thing means, and this is the reason why ice at 0 degrees Celsius is more effective in cooling than water at 0 degrees Celsius. That means if I have ice maintained at 0 degrees Celsius and I also have water maintained at 0 degrees Celsius, just by looking at the temperature, what we will think? We will think that both of them will have similar cooling effect. But no, cooling effect of ice at 0 degrees Celsius is more, it is more effective when it comes to cooling than water at 0 degrees Celsius. Why? Because when ice was converting to water, ice must have absorbed some amount of heat, and that heat will be equal to the latent heat of fusion. So, water at 0 degrees Celsius have some amount of, like it is having more energy as compared to the ice at 0 degrees Celsius. Overall heat energy content of water at 0 degrees Celsius is more than the heat energy possessed by ice at 0 degrees Celsius, and that is why ice is more effective in cooling. And this is a very, very important point. A number of questions are asked on this. Okay, coming on to the reverse process of melting. Conversion of liquid to solid. Movement of any substance from its liquid state to solid state is known as freezing. The process is reverse of melting, and it is defined as a process in which a liquid converts into solid state at atmospheric pressure and at a specific temperature. This temperature is definitely known as freezing point, the temperature at which a substance actually freezes. The substance actually converts from liquid to solid state is known as its freezing point, and the simplest example can be freezing of water. What happens when we keep water into ice? We fill water into ice trays and we keep it in refrigerator. It freezes in some time. And I said some time because it takes time. The water will not convert to ice as soon as you keep it inside the fridge. No, it takes some time. We fill the ice trays, we keep them in refrigerator. It takes at least 3 to 4 hours to convert water into ice. What happens during these 3 to 4 hours? During these 3 to 4 hours, the temperature of the water decreases. What happens? The temperature of the water will decrease. Slowly, the temperature will decrease, and the temperature will reach up to the freezing point. At a specific temperature, only the freezing will take place. So what happens during this duration where the temperature is continuously decreasing? Actually, when the temperature of a liquid is lowered, that means as soon as you start cooling a liquid, its temperature is lowered, and with the decrease in temperature, the kinetic energy also decreases. With the decrease in kinetic energy, the movement becomes restricted, and at freezing point, the kinetic energy is sufficiently low to stop the movement of particles, and at that moment, the attractive forces pull the particles together and fix them in fix them at their positions to convert liquid into solid. So again, kinetic energy is playing a very important role. When we cool, the kinetic energy decreases. As the temperature goes down, the kinetic energy keep on decreasing, and at a specific point, at a specific temperature known as freezing point, what happens? The attractive forces pull the particles together and the liquid freezes. The attractive forces again come into picture because the kinetic energy is now low, so attractive forces will dominate and the particles will be pulled together, fixed at their positions, liquid will be converted to solid state. So this is how freezing takes place, and the freezing point is the temperature at which liquid freezes to become solid at the atmospheric pressure. The numerical value for freezing point and melting point of a liquid remains same. The melting point of water and the melting point of ice and freezing point of water are same. Ice melts at 0 degrees Celsius and water also freezes at 0 degrees Celsius, and the value in kelvins is 273 kelvins. Coming on to the vaporization. Vaporization is the process which refers to change of state from liquid to gaseous state. So you can say that the process in which a liquid changes in the gaseous state by absorbing heat energy. Now, the heat energy may be absorbed from the surrounding air or it could be provided. If we want to boil, we need to provide energy and take the temperature to a specific value known as boiling point. But if we simply leave some liquids, they evaporate. So they vaporize on their own, absorbing the heat energy from the surroundings. So whether it is evaporation taking place or boiling taking place, the liquid will be absorbing heat energy and will be converting to gaseous state. So we will go in, we'll talk in general for now. So the process in which a liquid changes into the gaseous state by absorbing heat energy is known as vaporization. Simplest could be the conversion of water to water vapors, isn't it? Water vapors, or sometimes we call steam. We say steam is the gaseous state of water. So water, when is heated, when it absorbs heat energy, gets converted to its own gaseous state. And again, what causes vaporization? What is the reason behind vaporization? Again, kinetic energy has got a lot of things to do here. When we heat a liquid, what will happen? What was happening when we heated a solid? When we heat a solid, the kinetic energy of the particles of solid increases and they start vibrating at a greater speed and greater frequency. Similarly, when we heat a liquid, the kinetic energy of the particles increases and slowly kinetic energy will keep on increasing with the heating. At a moment, kinetic energy will become sufficiently high to overcome the attractive forces existing in between the particles of a liquid, and the particles will break free from each other. They will be now free to move in random directions and liquid will convert to gaseous state. Okay? And the temperature at which a substance starts boiling is known as its boiling point. There is no specific temperature at which evaporation takes place. Evaporation can take place at any temperature below the boiling point of the liquid, but boiling takes place at a specific temperature, and boiling point is the measure of strength of attractive forces between the constituent particles of a liquid. By looking at the value of boiling point, you can easily comment on the strength of attractive forces existing in between the particles of a liquid. Higher the value of boiling point, more is the strength of attractive forces. Obviously, again, if the particles of liquid are held together through strong forces, more heat energy will be required to overcome. Okay, so higher the boiling point, higher is the strength of attractive forces existing in between the particles of a liquid. So just by looking at the boiling point of a liquid, you can comment on the attractive forces, strength of attractive forces between its particles. Now coming on to two important terms, volatile liquids and non-volatile liquids. See, liquids can be divided into two categories, volatile and non-volatile. The liquids having low boiling point are known as volatile liquids, and liquids having high boiling points are known as non-volatile liquids. You must have seen that a few liquids evaporate on their own very quickly. Okay, the nail polish remover that we use, or the petrol, what happens? The petrol, as soon as it is exposed to the external environment, it evaporates. If you take some petrol in an open dish, it will evaporate in some time. If you spill water on a table or on the floor and you leave it, the water will evaporate on its own in some time, isn't it? Such liquids are known as volatile liquids. But consider the example of glycerin here. You take some amount of glycerin, leave it in an open dish, will it evaporate on its own? No, it will remain as it is. The quantity will not decrease. This happens because the boiling point of glycerin is quite high. It is not able to evaporate easily. Hence, we label it as non-volatile. And each and every pure liquid has a fixed value of boiling point, which could be used as one of the identification characteristics for that liquid. And in a similar way, we can use the melting point of a solid as the identification characteristic for solid. If we want to identify, if we want to perform some preliminary test for identification of a solid, melting point determination is one of them. Okay, now coming on to latent heat of vaporization. The way we understood about the latent heat of fusion, similarly you need to understand about the latent heat of vaporization. And how do we define this term? Latent heat of vaporization is defined as the amount of heat which is required to convert 1 kg of liquid into gas at atmospheric pressure and at its boiling point. Okay, try to recall about the latent heat of fusion. I told you that the amount of heat which is required to convert 1 kg of solid into liquid at its melting point is known as latent heat of fusion. So similarly, when you boil a liquid, the amount of heat which is required to convert 1 kg liquid into gaseous state at the melting point is known as latent heat of vaporization. Suppose if I talk about water, the latent heat of vaporization is 540 kilocalories per kg. What does this mean? This means that maintaining the temperature at 100 degrees Celsius, you have 1 kg water, you increase its temperature, bring it up to 100 degrees Celsius and maintain the temperature at 100 degrees Celsius. While maintaining the temperature of 1 kg water at 100 degrees Celsius, the amount of heat which will be required to convert that 1 kg water into the gaseous state is the latent heat of vaporization for water. So similarly, for each and every liquid, the amount of heat which is required to convert its 1 kg into gaseous state, maintaining the liquid at its boiling point, is known as latent heat of vaporization. And there's again a very important point to remember, that steam at 100 degrees Celsius is more effective in heating as compared to the water at 100 degrees Celsius. Okay, that means if I have steam maintained at 100 degrees Celsius and I have water also at 100 degrees Celsius, steam will have more heat content. Okay, so overall heat content inside the steam is more as compared to the heat content in water at 100 degrees Celsius, because water after reaching 100 degrees Celsius absorbs some extra amount of heat, that is the latent heat of vaporization, and then it is converted to steam. So steam have some, like it is having little more amount of heat energy as compared to water, even if they are maintained at the same temperature. So that is the reason why steam causes more severe burns as compared to water, even when both of them are maintained at same temperature. This is a very, very important question which is asked in exams. So I hope now you all will be able to write answer to this question properly based on your understanding about the latent heat of vaporization. Okay, so this is how we can graphically represent and understand. See, in this graph, heat supplied is plotted on the x-axis and temperature is plotted on the y-axis. Initially, suppose we have a substance in the solid state. Initially, when we start heating that substance, the temperature also starts increasing. See, the temperature is increasing. But after some time, the temperature becomes constant for some duration of time. Isn't it? For some duration of time, the temperature is constant. What is actually happening in this duration of time? The solid is actually converting to liquid state. So, actual change of state takes place here. And see, the temperature is constant. Similarly, as soon as all the solid is melted with the, and here also we are supplying the heat, isn't it? So, this much is the latent heat of fusion. This much amount of heat is utilized in overcoming the forces of attraction and not increasing the temperature. See, the value of heat is increasing, but the value of temperature is constant. As soon as all the solid available is converted to liquid state, again with the increase in heat supplied, the temperature will start rising, and again after some time it will become constant for a specific duration of time. During this duration, what is happening? During this duration, liquid is actually converting to gaseous state. The actual boiling is taking place at this in this particular duration, and this much amount of heat will be latent heat of vaporization. As soon as all the liquid is converted to gaseous state, temperature will again start rising. That means temperature remains constant during the phase transition. Whenever solid melts to liquid, during that duration of time, when this melting is actually taking place, the temperature will remain constant. And the heat supplied in that duration of time will be known as latent heat of fusion. And similarly, you can understand about latent heat of vaporization. Okay, coming on to the next process, condensation. What is condensation? Condensation is a process in which gas changes into liquid by giving out heat energy, and this process is known as condensation. It is the reverse of vaporization. Vaporization was conversion of liquid to gas. So, conversion of gas to liquid is known as condensation. Simplest example could be conversion of water vapors to liquid state on decrease in, like whenever the water vapors are cooled. This is how clouds are formed in the atmosphere, isn't it? The water vapors rises up in the atmosphere, the temperature decreases, water vapors condense, and minute water droplets collect, and when there is sufficiently large amount of water, they fall down, isn't it? So, condensation is the conversion of any substance from its gaseous state to liquid state. Condensation point. This is the temperature at which condensation actually takes place. Water vapors does not convert back to water at any temperature. They again need a specific temperature at which the condensation will take place, at which this phase transition will take place, and the numerical value of condensation, the temperature at which condensation takes place and boiling takes place, is the same, isn't it? Now coming on to a very important and interesting process known as sublimation. Sublimation is the process of conversion of solid state directly to the gaseous state. Okay, there are a few substances which do not move into the liquid state on heating. Those substances directly change into their vapors. So, the process in which a solid directly changes to the gaseous state without passing through the liquid state is known as sublimation. What do we expect? We expect a solid to melt when we heat it. And then when we heat the liquid, it is expected to convert to the gaseous state. But for a few substances like naphthalene, iodine, camphor, ammonium chloride, dry ice, when we heat these substances, they directly move to their gaseous state. They do not move to their liquid state. Such substances are known as sublimable substances, and the process is known as sublimation. If I give you example, these are naphthalene balls. Iodine, the crystals of iodine are purple in color. Camphor, that means kapoor. Ammonium chloride is a chemical substance with the formula NH4Cl, and dry ice is the solid form of carbon dioxide gas. Okay, dry ice is solid CO2. So, all these are the substances which sublime. That means if you will heat them, they will not move to their liquid state, they will not melt, they will directly vaporize, they will directly convert to their gaseous state. This process is known as sublimation. And for a few substances, the reverse also takes place. A few substances from their gaseous state directly moves to their solid state. The example is carbon dioxide gas. We'll understand about it in detail, but yes, if we try to liquefy carbon dioxide gas, rather than moving into the liquid state, it directly moves to the solid state. The process is known as deposition. What do we call it? We call it deposition. So conversion, direct conversion of a gas to solid without changing into liquid state is known as deposition. So sublimation and deposition are opposite of each other. Solid to gas directly is sublimation. Gas to solid directly is deposition. Okay. And the smoke, I was talking about dry ice to every one of you. The smoke that appears on the stage in the live shows. What is that? Dry ice is actually used. Dry ice is having a property of sublimation. So as soon as its temperature is increased and pressure is reduced, it sublimes. And the dense fumes of carbon dioxide are seen like white color fumes. So dry ice is used for this particular purpose. So what is sublimation? Sublimation is conversion of a solid directly to the gaseous or vapor state without passing into the liquid state. And the reverse of it is deposition. Okay. Coming on to the liquefaction of a gas. Liquefaction of a gas refers to obtaining a gas into the liquid state. So there are a number of gases like oxygen, nitrogen. These are the elements which exist in gaseous state, isn't it? But we have heard about liquid oxygen cylinders, liquid nitrogen cylinders. So how do they obtain these substances in their liquid state? Converting a gaseous substance into its liquid state is possible by bringing about a change in the pressure or temperature or a combination of both the mentioned factors. That means most of the time we need to change the temperature as well as the pressure to obtain a gas into the liquid state. Let me tell you that we need low temperature, okay, and high pressure. These are the conditions which are required for conversion of a gaseous substance into its liquid state. So these are the conditions for liquefaction of gas. Whenever we want to obtain a gas in the liquid state, what we do, if we have this gas, we first of all cool it. So the first step in the liquefaction process is cooling. Okay, the first step is cooling. I will write cool here. After cooling, what we get? We get the cooled gas. We get the cooled gas we obtain. And on this cooled gas, when we apply high pressure, we obtain the gas in the liquid state. Okay. So what we do in the first step, we cool it. And while cooling, we ensure that the gas is cooled up to a specific temperature. Yes, it is compulsory to bring a gas down to a specific temperature before applying high pressure on it. Otherwise, no matter how high pressure you apply, it will not liquefy. Yes. So that temperature is known as critical temperature. The temperature up to which you need to cool the gas compulsorily, because above that temperature, the gas cannot be converted into liquid no matter how high pressure you apply. So that temperature is known as critical temperature. So the process of liquefaction of a gas starts with cooling. And we cool gas up to a specific temperature known as critical temperature. Different gases have different value for critical temperature. So first of all, what we do, we take gas, we start cooling it. We'll cool it up to its critical temperature. We will maintain the gas at its critical temperature or below it. And maintaining the gas at its critical temperature, we apply high pressure on it. So the pressure at which gas liquefies, the gas which is maintained at its critical temperature, it liquefies at a specific value of pressure, and that pressure is known as critical pressure. So you can say that the pressure which is required to convert a gas into liquid state at its critical temperature, that means you need to maintain the gas at a specific temperature. That temperature is critical temperature. So the pressure is known as critical pressure. Now, example of deposition if I talk about, I was talking about carbon dioxide gas, and I told you as soon as we try to liquefy the carbon dioxide gas by cooling it and applying high temperature on it, what we will do? We will cool the gas, we will bring it to its critical temperature. After that, we'll start applying high pressure on it. Not high temperature, we will apply high pressure on it. So what we will expect? We will expect that carbon dioxide will be converted to its liquid state. But carbon dioxide directly moves into its solid state. What we obtain? We obtain dry ice. This is how dry ice looks like. Okay. So this is an example of deposition where the gas is directly moving to its solid state. Okay. Now I have a practice question for every one of you. What is the question? It is about the formation of clouds, and you know which process is involved in formation of clouds. The process of condensation is involved. So based on your understanding from today's session, you should be able to write answer to small logical questions. Okay. In addition to this question, I am giving you a few more questions as homework. What I expect you all to do? I expect you all to write answer to all these questions based on your understanding from today's session. And I'm pretty sure that you all will be able to write answers to all these questions. Total 9 questions are there. Okay. So please try to write answers to all these questions. And now let's quickly recap what we have discussed and understood in today's class. We discussed about the interconversion of states of matter. We discussed in detail all the processes associated with change of state of any matter and all the related concepts like latent heat. We discussed about the liquefaction of gases, freezing point, melting point, all the different temperatures, and we also discussed about volatile and non-volatile liquids. I hope every one of you properly understood everything in today's session. That is all from my side. Thank you.